Hey there, have you ever looked up at the night sky and felt a profound sense of wonder? Those tiny, shimmering points of light hold incredible stories. Today, we're embarking on a gentle exploration, a quiet journey into the heart of starlight itself. We'll uncover its ancient secrets. Before we delve into the cosmos, if you enjoy these explorations, please take a moment to like this video and subscribe to our channel. It helps us share more science. Imagine a clear, moonless night, the kind where the stars seem to stretch endlessly, each one a pinprick of pure, unfathomable light. A scientist, perhaps an astronomer, stands quietly gazing upwards. Her breath makes a faint mist in the cool night air. She picks out a single star, not the brightest, but one that holds a particular, steady glow. It seems to beckon, a distant beacon. A simple question forms in her mind, one that has echoed through human history. What exactly is that light? Where does it begin its journey? It's not just a point of light, it's a message, traveling across unimaginable distances, a story whispered across the cosmic void. Every photon, every particle of light reaching our eyes has undertaken an epic voyage, a journey spanning light years. Think of it, the light we see tonight left its home star perhaps hundreds, even thousands of years ago. It carries with it information about its origin, a snapshot of a moment long past, a true cosmic time capsule. This light traveled through the silent, cold vacuum of space, uninterrupted for countless millennia. But how does a star create such powerful, enduring light? What is the engine behind this cosmic glow? Deep within the heart of every star, an incredible process unfolds, nuclear fusion. It's the star's gentle, powerful furnace. Under immense pressure and searing temperatures, hydrogen atoms combine to form helium. This reaction releases a tremendous amount of energy. This energy takes the form of light and heat born in the star's fiery core. It's the very essence of starlight. Imagine tiny packets of this energy, called photons, beginning their slow, tortuous climb from the star's interior. It's not a direct path. Photons collide and scatter, taking hundreds of thousands of years to reach the star's surface. Once free from the star's gravitational grasp, the journey truly begins, an unimpeded sprint across the cosmos. This light travels at the fastest speed possible in the universe, the speed of light itself, approximately 186,000 miles per second. It's a constant, unwavering pace, covering billions of miles every single hour, year after year, century after century. There are no obstacles in the vast emptiness between stars, no resistance to slow its incredible journey. This light is ancient. The photons hitting our eyes now carry the signature of events that unfolded long, long ago. For some stars, the light we see began its journey before humans even walked the earth. It's a tangible link to the past, a direct connection to the universe's earliest moments and its ongoing evolution. This journey of light is not just a scientific fact, it's a poetic reminder of our place in the cosmos. Each twinkling star is a messenger, bringing news from distant realms, from eras long past. The light from our sun, for example, takes about 8 minutes to reach us, a relatively quick trip. But for the stars we observe in the night sky, those minutes become years, decades, centuries. The nearest star system, Alpha Centauri, is over 4 light-years away. Its light takes over 4 years to reach us. So when we look at Alpha Centauri tonight, we are seeing it as it was 4 years in the past. This concept of looking back in time is fundamental to astronomy. The universe reveals its history through light. The light from a distant galaxy can take billions of years to reach our telescopes. We are seeing it as it appeared near the dawn of time. This long, undisturbed journey through the vacuum of space is critical. It preserves the light's original information. It's only when this ancient light finally encounters our planet's atmosphere that its journey becomes more complex. Until that point, the light has been a pure, unadulterated signal from its stellar source. Our atmosphere, a thin, protective veil, is where the light story begins to change. It's where the twinkle is born. But that, my friends, is a story for our next chapter. For now, let's marvel at the sheer scale of Starlight's journey. The light you see tonight has traveled across unimaginable distances, a silent testament to the universe's grandeur. It's a profound connection to the past, a gentle glow that reminds us of the endless mysteries waiting to be explored. The ancient light, having journeyed across the cold, silent vacuum of space for millennia, finally reached its destination, our vibrant, living planet. Its long, undisturbed voyage was at an end. Now it was about to encounter something fundamentally different from the emptiness it had known. This was Earth's atmosphere, a thin, protective veil, yet a dynamic and complex envelope of gases surrounding our world. It is within this embrace that the steady, distant glow of starlight transforms into the familiar, dancing twinkle we observe. Imagine this atmosphere not as a uniform, still blanket, but as a vast, shimmering curtain, constantly in motion. It's a turbulent ocean of air, driven by the sun's heat, Earth's rotation, and the interplay of land and sea. Within this atmospheric ocean, there are countless pockets of air, each with slightly different temperatures and densities. Warm air rises, cool air sinks, creating invisible currents and eddies that constantly shift and reform. Think of the shimmering heat haze you sometimes see rising from a hot road on a summer day. That visible distortion is caused by light bending as it passes through air of varying temperatures and densities. Our entire atmosphere is filled with such invisible, shifting pockets, though on a much grander, more complex scale. As starlight plunges into this dynamic medium, its undisturbed journey ends, and a new interaction begins. Light, as we know, travels in straight lines through a uniform medium, like the vacuum of space. However, when light passes from one medium to another, or through regions of varying density, its path changes. This bending of light is a phenomenon known as refraction. It's the same principle that makes a spoon appear bent in a glass of water. Each pocket of varying temperature and density in our atmosphere acts like a tiny, imperfect lens. As starlight encounters these ever-shifting atmospheric lenses, its path is gently but constantly redirected. One moment, the light might be bent slightly towards us, appearing brighter. The next, it might be bent away. This continuous, subtle redirection means the star's light isn't arriving at our eyes in a steady stream. Instead, it's flickering, its apparent brightness and position shifting ever so slightly, many times each second. This rapid fluctuation in brightness and apparent position is what we perceive as the star's twinkling. It's a beautiful, observable phenomenon, a direct consequence of Earth's atmospheric dance. Scientifically, this effect is known as stellar scintillation, derived from the Latin scintillare, meaning to sparkle. It's important to remember that the stars themselves are not actually twinkling. Their light is constant. The twinkle is entirely a local phenomenon, happening within the last few miles of the light's journey. An astronaut above the atmosphere would see stars as steady, unwavering points of light, like tiny, perfect diamonds. This atmospheric interference is more pronounced when stars are low on the horizon, as their light must travel through more air. Conversely, stars directly overhead twinkle less because their light traverses a thinner column of air. The conditions of the night sky also play a role. A calm, stable atmosphere leads to less twinkling. Windy, turbulent nights, however, amplify the effect, making stars dance with greater vigor. For astronomers, this twinkling, while beautiful, presents a significant challenge to precise observation. It blurs images, making it harder to discern fine details of distant celestial objects. This atmospheric distortion is why major observatories are often built on high mountains, above much of the densest air. Even there, the remaining atmospheric turbulence still affects the clarity of telescopic views. Scientists have developed ingenious methods like adaptive optics to counteract this natural blurring effect. These systems use deformable mirrors to correct the incoming starlight, removing the atmospheric dance in real time. So the next time you gaze at a twinkling star, remember it's not the star itself dancing. It's our own Earth, its dynamic atmosphere, performing a gentle ballet with light from across the cosmos. This atmospheric embrace shapes what we see, adding a layer of complexity to the ancient messages carried by starlight. But what about other celestial bodies? Do planets also twinkle, or do they hold a steadier gaze in our night sky? The question lingered in the cool night air. If stars twinkled due to our atmosphere, what about the planets? Do they too dance with the shifting currents of air? An observer, perhaps a seasoned astronomer, would notice a profound difference almost immediately. The stars glittered, their light a lively, flickering spectacle. But among these dancing pinpricks, certain celestial bodies held a steady, unwavering glow. These were the planets, serene and constant in their light. Venus, Jupiter, Mars each shone with a calm, almost placid illumination, a stark contrast to the restless shimmer of the distant stars. This observation was not merely anecdotal, it was a fundamental clue, a subtle whisper from the cosmos about the true nature of light and distance. The key to understanding this difference lies in how we perceive these objects, or more precisely, their apparent size in our sky. Stars, despite their immense actual size, are incredibly far away. To our eyes, even through powerful telescopes, they remain effectively pinpoints of light. Imagine a tiny, perfect bead of light so far away it occupies almost no physical space in our field of vision. Planets, however, are much, much closer to Earth. They are still vast distances away, but comparatively, they are our cosmic neighbors. Because of this closer proximity, planets appear not as pinpoints, but as tiny, discernible disks of light when viewed through a telescope. Even to the naked eye, this difference in apparent size, though imperceptible as a disk, is crucial to how their light interacts with our atmosphere. Think of it like this: a distant flashlight looks like a single bright dot, but a closer one reveals the full circular beam. The star's light is a single, slender thread arriving from an immense distance, a solitary ray entering our turbulent air. The planet's light, by contrast, is a broader beam, a tiny but measurable patch of light, even if it's just a fraction of an arcsecond wide. This distinction between a point source and an extended source of light is fundamental to understanding stellar scintillation. As we learned, our atmosphere is a dynamic tapestry of air pockets, constantly shifting, each acting like a tiny, imperfect lens. When the pinpoint light from a star encounters one of these turbulent pockets, its entire path can be momentarily bent or scattered. One instant, the light might be refracted directly into our eye. The next, that same pocket of air might bend it slightly away. Because the star's light is so concentrated, a single atmospheric disturbance can effectively push the entire image of the star off our retina. This rapid flickering in and out of our line of sight, combined with changes in brightness, creates the characteristic twinkling effect. It's like trying to catch a single drop of rain in a strong, gusty wind. It's difficult to predict where it will land. The star's light is either there, or it's not, or it's slightly dimmer or brighter, all within fractions of a second. Each atmospheric bubble, each thermal eddy, acts as a tiny prism, momentarily redirecting the star's entire contribution of light. This constant, chaotic redirection is precisely why stars appear to dance so vigorously in our night sky. The atmosphere's embrace, while beautiful, is a turbulent gauntlet for these ancient, distant messages. Now consider the planets. Their light originates from a wider apparent disk, not a single point. Instead of a single thread, many parallel rays of light are arriving from different parts of that tiny planetary disk simultaneously. When these multiple rays encounter atmospheric turbulence, some might be bent away, while others are bent towards us. However, because the planet's light comes from an extended source, the overall effect of these individual distortions is averaged out. Imagine a large sheet held by many hands in a gusty wind. While individual sections might flap, the sheet as a whole remains largely visible. The light from one edge of the planet's disk might be temporarily dimmed, but light from another part of the disk compensates. The numerous light paths essentially smooth out the atmospheric disturbances, leading to a much steadier apparent glow. So while the atmosphere still affects planetary light, the impact is spread across many light paths rather than a single, critical one. The subtle distortions that do occur are usually too small and too rapid for our eyes to perceive as twinkling. Instead, we see a calm, consistent light, a beacon of stability amidst the celestial dance of the stars. This simple observation, the difference between a twinkling star and a steady planet, is a powerful lesson in astronomical physics. It teaches us not only about the nature of light and distance, but also about the ever-present, dynamic influence of our own atmosphere. It's a testament to the fact that what we perceive is often a complex interplay between the source of light and the medium through which it travels. The universe, in its elegant complexity, provides these subtle clues, allowing us to decipher its grand mechanisms with careful observation. But beyond these basic distinctions, how do we use these atmospheric effects to our advantage? Can we learn more from the very turbulence that obscures our view? The human spirit, ever curious, refused to be limited by the atmosphere's veil. For centuries, our gaze has been drawn upwards, seeking to pierce the shimmering barrier with increasing clarity. Early stargazers used simple tools, charting the heavens with diligent patience. Yet, the desire to see more, to resolve fainter details, remained a powerful, persistent urge. Then came the telescope, a revolutionary invention that transformed our understanding. Suddenly, the heavens unfolded with unimaginable richness, though still imperfectly. It was a new window, a tool that magnified the distant light, bringing the faint whispers of the cosmos closer to our grasp, but the air still danced. Galileo, with his modest instrument, revealed the moons of Jupiter and the phases of Venus, forever changing our perception of our place in the universe. Each new observation brought moments of breathtaking clarity, quickly followed by the frustration of atmospheric shimmer, blurring the delicate structures of nebulae and galaxies. The very air that sustained life on Earth also obscured our deepest cosmic vision, a persistent, dynamic veil that distorted the incoming starlight. This challenge ignited a new quest, to find ways to peer through the atmospheric turbulence to achieve truly pristine views of the universe's grand tapestry. Patience and ingenuity became paramount. Scientists pondered the nature of this atmospheric interference, seeking patterns in its chaotic dance, hoping to find a countermeasure. The first major realization was simple yet profound: location mattered. The less atmosphere between the telescope and the stars, the better the view. This understanding led astronomers to seek out the highest, driest, and most stable environments on Earth, remote mountain peaks, far from city lights and turbulent weather. Perched atop these natural pedestals, observatories were built, monuments to human ambition, designed to rise above much of the thickest, most turbulent air. At these elevations, the column of air above the telescope was significantly thinner and often calmer, reducing the amount of atmospheric distortion. The images captured from these lofty sights were indeed clearer, the stars less prone to violent twinkling, allowing for more detailed studies of distant galaxies and nebulae. Places like Mauna Kea in Hawaii or the Atacama Desert in Chile became prime locations, offering unparalleled ground-based viewing conditions, though never entirely free of Earth's influence. Life and work in these remote, high-altitude observatories demanded resilience, a testament to the dedication of those who sought to unravel the universe's secrets. In the quiet hum of the domes, scientists meticulously collected data, their observations pushing the boundaries of what was known, one steady image at a time. Even at these heights, a subtle shimmer persisted. The upper layers of the atmosphere, though thinner, still contained pockets of varying temperature and density, causing some light distortion. The twinkle was diminished but not entirely vanquished. The remaining atmospheric dance still limited the ultimate resolution achievable by ground-based instruments. It was a significant step forward, a partial victory in the battle against atmospheric blurring, but the yearning for absolute clarity continued to drive innovation. The most direct solution, then, was to escape the atmosphere entirely, to place telescopes where the air could never interfere in the silent vacuum of space. This ambitious vision led to the development of space telescopes, instruments designed to orbit our planet, offering an unhindered view of the cosmos. The dream was immense, to capture starlight before it ever encountered Earth's turbulent air, preserving its pristine journey, its ancient messages. The Hubble Space Telescope became the most iconic example. Launched in 1990, it revolutionized astronomy with its incredibly sharp, detailed images. Hubble delivered views of distant galaxies and nebulae with unprecedented clarity, revealing structures and details previously only imagined, free from any atmospheric twinkle. Through Hubble's eyes, stars appeared as perfect, unwavering points of light, their inherent brilliance revealed without the terrestrial dance that so captivated ground-based observers. Its deep-field images, capturing light from the very early universe, unlocked secrets about galaxy formation and the grand evolution of the cosmos. Other space observatories, like the more recent James Webb Space Telescope, continue this legacy, each designed to explore different wavelengths of light, expanding our cosmic understanding. Yet, space telescopes are immensely complex and costly endeavors, requiring colossal investment and years of meticulous planning and execution. They are not easily replaced or repaired. While offering unparalleled views, they present their own set of engineering and logistical challenges, reminding us that every solution brings new complexities. But the quest for clearer views from asterisk within asterisk Earth's embrace did not cease. A remarkable innovation, adaptive optics, offered a new path forward for ground-based astronomy. Adaptive optics is a brilliant strategy to actively counteract atmospheric distortion in real time, effectively untwinkling the stars for powerful ground telescopes. The atmosphere's turbulence shifts hundreds of times per second. Adaptive optics systems must respond with equal speed and precision to be effective. At its heart is a flexible, deformable mirror covered with hundreds or even thousands of tiny actuators. These actuators can push and pull the mirror's surface, changing its shape. To know how to deform the mirror, the system needs to measure the distortion. It does this by observing a guide star, either a natural bright star or an artificial one created by a laser. Light from this guide star passes through the same atmospheric turbulence as the target celestial object. A wavefront sensor measures how distorted this light has become. A computer then processes this information instantly, sending commands to the actuators on the flexible mirror. The mirror deforms, correcting the incoming light's wavefront. This correction happens many times per second, dynamically reshaping the mirror to perfectly compensate for the ever-changing atmospheric blur, as if adjusting dynamic eyeglasses. With adaptive optics, ground-based telescopes can achieve image clarity comparable to, and sometimes even surpassing, that of space telescopes for specific observations, opening new avenues of discovery. This blend of human ingenuity and technological prowess allows us to pierce the veil, revealing the universe with astonishing detail, bringing us closer to the deeper stories hidden within Starlight's ancient glow. We have learned to tame the atmosphere to see the stars with unblurred clarity, but the true quest extends beyond mere focus, beyond the twinkle. For Starlight carries more than just its brightness or its dance across our sky. It holds a profound language waiting patiently to be deciphered. Imagine light not just as a single, uniform beam, but as a complex tapestry, intricately woven with threads of different colors and energies. Each star, though appearing to our naked eye as a white point, possesses its own distinct hue, a subtle hint at its inner workings. From the fiery reds of aging giant stars to the brilliant blues of young, hot stars, color is the first visible clue to their nature. But the richest cosmic stories are not told by color alone. They are hidden deeper within the light's very composition, its spectral fingerprint. For centuries, scientists pondered how to truly unlock these secrets. How could we read the light itself to understand its source? The answer lay in a simple yet profound principle: splitting light. Just as a prism separates white light into its component rainbow of colors. This process, called spectroscopy, takes the light from a distant star and precisely spreads it out into its constituent wavelengths. What emerges is often not a continuous rainbow, but a spectrum marked by distinct dark or bright lines, like a unique cosmic barcode. These spectral lines are the universe's own alphabet, each one corresponding to specific elements interacting with the starlight. When light from a star passes through its cooler outer layers, certain wavelengths are absorbed by the specific elements present there. This absorption creates the dark lines we observe, telling us precisely which elements exist in the star's atmosphere and surrounding gas. Hydrogen, helium, carbon, oxygen, the fundamental building blocks of the cosmos, all leave their distinctive, unmistakable mark. By analyzing these unique patterns, astronomers can determine the chemical composition of stars and nebulae, even those light years away. It's like reading the ingredients list of a cosmic recipe, understanding its nature without ever needing to touch it. Beyond composition, spectroscopy also reveals a star's temperature. Hotter stars emit more blue light, cooler ones more red. The intensity and distribution of light across the spectrum are precise indicators of its surface temperature and energy output. This allows us to classify stars into different types, understanding their life stages and evolutionary paths across cosmic time. But Starlight holds even more dynamic information, the tale of motion through the vast, silent cosmic ocean. Imagine the sound of an ambulance siren. As it approaches, the pitch rises. As it moves away, the pitch drops. This familiar phenomenon is the Doppler effect, and it applies to light waves just as it does to sound waves. If a star is moving towards us, its light waves are subtly compressed, shifting its spectral lines towards the bluer end of the spectrum. This is blue shift. Conversely, if a star is moving away, its light waves are stretched, shifting its spectral lines towards the redder end of the spectrum. This is redshift. By precisely measuring these subtle shifts in the spectral lines, astronomers can determine a star's velocity relative to Earth. This radial velocity method has been revolutionary, allowing us to detect the gravitational tug of unseen companions. One of the most profound discoveries powered by this technique is the existence of exoplanets, worlds orbiting other stars. A star with an orbiting planet will wobble slightly due to the planet's gravitational pull. This wobble causes a tiny, periodic Doppler shift. For decades, these distant worlds were pure speculation. Now, through Starlight's subtle whispers, we've found thousands. Starlight also holds the grand narrative of the universe itself, revealing its origins and its ultimate, unfolding fate. The redshift of distant galaxies, for example, tells us they are rushing away from us, a clear sign of an expanding universe. This cosmic expansion, inferred directly from the light of far-off celestial objects, is a cornerstone of modern cosmology. We can even trace the life cycle of stars, from their birth in nebulous clouds to their explosive deaths as supernovae. The elements forged in the hearts of stars and scattered by these explosions become the raw material for new stars and planets. Every atom in our bodies, every element on Earth, was once part of a star, synthesized in its fiery core or explosive demise. Starlight, therefore, is not just a source of illumination, but a profound, tangible link to our own cosmic ancestry. It is a library of cosmic history, each photon a word, each spectrum a chapter, detailing the ongoing saga of creation. The quiet dedication of scientists painstakingly analyzing these spectral fingerprints slowly unravels these epic stories. From the composition of a distant nebula to the speed of a receding galaxy, Starlight is our ultimate guide to the universe. And as we continue to listen to its ancient whispers, we prepare for the next revelations, the next chapter in our cosmic understanding. Our journey began with a simple flicker, a tiny dance in the vast canvas of night. The twinkling star, a familiar sight, held an unspoken question. We sought to understand this dance, to move beyond mere observation into the intricate physics that governed its subtle shifts. We traced the Starlight's epic voyage from the fiery heart of a distant sun, where fusion's gentle power ignited its ancient glow. Across unimaginable cosmic distances, through the silent, empty vacuum, this light traveled for centuries, undisturbed. Then, its encounter with Earth's atmosphere, a turbulent, shimmering ocean of air, began to bend and redirect its path. This atmospheric dance, the continuous refraction through pockets of varying temperature and density, was the true source of the twinkle. We learned why stars, distant pinpoints, twinkled so vigorously, while closer planets, appearing as tiny disks, held a steady gaze. The difference lay in their apparent size, how much of our atmospheric turbulence each celestial body's light had to contend with. This simple distinction was a profound lesson in astronomical perception, revealing the subtle interplay of light and medium. Our quest for clarity led us to mountaintops, seeking thinner air, and eventually beyond our planet's embrace into space itself. The Hubble Space Telescope offered pristine views, stars unwavering, revealing the universe with unprecedented sharpness. Yet even from Earth, ingenuity prevailed. Adaptive optics emerged, a triumph of technology to untwinkle the stars in real time. This allowed ground-based instruments to achieve astonishing clarity, correcting the atmosphere's dynamic distortions. We learned to split starlight to read its spectral fingerprint, decoding the elements, temperatures, and motions of distant celestial bodies. Each spectral line whispered tales of hydrogen, helium, and heavier elements, forged in stellar furnaces scattered by cosmic events. The Doppler effect in light revealed stars approaching or receding, even detecting the subtle wobble of exoplanet hosts. Starlight became a cosmic historian detailing the expansion of the universe, the birth and death of galaxies. Every photon carried a story, a fragment of the universe's grand, unfolding narrative waiting for us to patiently listen. Our initial wonder at a simple twinkle had blossomed into a profound understanding of cosmic mechanisms and our place within them. The journey of discovery had been long, filled with careful observation, persistent inquiry, and moments of breathtaking insight. And yet, as we sought to overcome the atmospheric veil, we found a deeper appreciation for its very existence. For the same turbulent blanket of air that makes stars twinkle is the very one that sustains life on our pale blue dot. It shields us from harmful radiation, provides the air we breathe, and maintains the delicate temperatures that allow life to flourish. The atmosphere is not merely an impediment to observation, it is an intimate part of our cosmic home, a protective embrace. Its dynamic nature, its constant motion, is a sign of a living, breathing planet connected to the sun's energy and the Earth's rotation. The twinkle, then, is a direct manifestation of this life-giving, protective shield, a signature of our terrestrial existence. It is a reminder that we are intrinsically linked to our planet, and through it, to the wider universe. Our efforts to pierce the veil were not to dismiss the atmosphere, but to understand its profound role in shaping our view. The atmosphere filters and transforms starlight, adding a unique terrestrial flavor to the cosmic message. It makes the universe feel personal, immediate, its ancient light filtered through the very air we breathe. And so, the twinkling star, once a simple mystery, then a scientific challenge, reawakens our gaze in a new light. The twinkle is no longer merely an impediment to be overcome, but a beautiful, gentle reminder of our cosmic home. It is a whisper from Earth itself, telling us of its dynamic embrace, its protective yet restless nature. Science, rather than diminishing wonder, deepens it, transforming a simple observation into a tapestry of interconnected phenomena. The night sky, even with its atmospheric dance, remains an endless source of inspiration, inviting perpetual curiosity. Every glimmer is an invitation to further discovery, a prompt to ask new questions, to seek deeper truths. The quest for understanding is never truly complete. It is an ongoing journey, passed from one generation of curious minds to the next. The universe continues to reveal itself in layers, each new insight opening doors to even grander mysteries. The twinkling of a star, once a puzzle, is now a poetic testament to the vibrant interplay between the distant cosmos and our living world. And so, as the moon climbs high, sleep well, knowing that even in the gentle flicker of a distant star, the universe whispers its endless, beautiful stories.